Hello everybody, Adam Lusek here, and I was recently browsing on Chroma's website, and that's ChromaDB, the super cool open source embedding database that I've been using recently, and I noticed a small little announcement that they had up here, launching MultiModal. So naturally I had to click in, and it turns out that they've now added some integrated functionality to use some open source embedding models that aren't just meant for embedding text, but actually images, and you can contain multiple modalities in a single embedding space. Which, what that means is that we can create now retrieval augmented generation pipelines using different modalities, not just the traditional text, but actually now images as well, using some cool open source models, and then we can combine them with some top of the line vision models to create some really fun flows. So that's what we're going to be going over today, is how to set up this sort of multimodal RAG flow with a focus on using pictures. So to provide a little bit of background and context before we jump into it, let's go over what a CLIP embedding function is and what OpenCLIP is. So CLIP originally comes from this paper that was released by OpenAI in January 5th of 2021, and this corresponding blog post, CLIP, Connecting Text and Images. And the simple one-liner of CLIP is that it stands for Contrastive Language Image Pre-training, and CLIP models basically connect images and text by learning from a wide variety of internet data, and that enables them to both understand and generate detailed descriptions of images and match images with corresponding text. This is all possible through the way that it's trained. And so during the training, these CLIP models actually learn to predict which images and texts are related by contrasting correct image text pairs against incorrect image text pairs. And what this does is it encourages the model to sort of create a shared embedding space where similar images and texts are close together and dissimilar ones are far apart. And what this allows is very, very robust zero-shot learning. And so what zero-shot learning is it's the ability for the model to then generalize this to new tasks or data without having to have seen them during training. This is super important because it allows the CLIP models to perform tasks it wasn't specifically trained for on the fly. For instance, it can now classify images into categories that it has never seen before by understanding the textual description of the categories. We're going to take advantage of this by being able to have the textual description be our user query, and then it will pull from our database of images to find the relevant ones. Long story short, this is effectively going to take the classic ability that text-based embedding models, similar to how you can have different chunks of text, submit a user query, and then it'll try and find these similar chunks of text to your user query. It's taking that same exact idea and then just applying it to photos. And these models, these CLIP models, are very much trained to be able to do this on photos. And while OpenAI's CLIP model is actually not public and not usable, people have taken the paper and recreated this essentially in an open source setting. So now there's this repo, OpenCLIP, that contains all sorts of open source CLIP-based models, these contrastive language image pre-training models that are able to do essentially the same thing, but now all open source. So this is what we'll be taking advantage of, and this is what ChromaDB takes advantage of. So hopping back to the code, I've got this nice diagram now, where essentially this is what we're going to be building. We're going to have a user query that's first going to go to a vector database that will pull photos, and then both the photos and the user query are going to go to a language model with vision capabilities, and then the language model will produce a final output. Super cool stuff. And so the first step to actually be able to do this is, of course, to get a relevant data set or some sort of collection of pictures that you actually want to do this from. And so I decided that I would make my life easy and just choose one from Hugging Face because there's a lot of image classification data sets already readily available on there. One that caught my eye that I thought was kind of cool was this Fashionpedia data set. And the Fashionpedia data set pretty much just has thousands of rows of images of just fashion. So cool stuff like that. And when I looked into it, it's really cool. It's a data set that consists of sort of two parts. It's an ontology built by fashion experts containing 27 main apparel categories, etc., etc. And then also a data set with 48,000 everyday and celebrity event fashion images annotated with segmentation masks and their associated per mask fine-grained attributes built by the Fashionpedia team. And so essentially they used this data set originally to train a model for classification and localized attribution of objects in fashion images. So given an image, their model will be able to classify what the image is about, different attributes about it, and then in sort of segmentized boxes, what's actually happening within those. So they've got a cool detailed website right over here, so you can check it out. They've even got an API to their stuff and whatnot. Some good, cool sponsors here. Really cool stuff. Check out their paper and whatnot. But they have a phenomenal open source database here that we're able to take advantage of. So essentially, I'm going to be using the Hugging Face dataset package to both load and prepare this data. So just using load dataset, I path over to the Fashionpedia dataset here. You can find any dataset where this is by clicking on the Use in Datasets library, and then it'll give you this little snippet of code and how to actually path over. Once we have that up, we can sort of select a sample image. So that'll be all in sort of different lists and dictionaries. And then I found out that using this string here will pull a relevant image. So just got a quick image there to show that. And then the next step is I'm actually just going to use a subset of this for this example. So I needed to have a way to grab some of the photos and just save them locally onto my drive. All I did was create a quick function where it'll path to a specific folder, this one that I'm calling Fashion Dataset. It will make that folder if it doesn't exist. And then the quick helper function that I have here will take in the dataset, the folder, and then the number of images that I want to save, which for this example, I'm just going to save the first 1,000 photos. And then it'll iterate through all of that, grab each image, and then save it there with just image, and then starting the index at 1 up to 1,000. So hopping over to that folder, that sort of just looks like this. We've just saved, thousands of, not thousands, but exactly 1,000 pictures of different fashion photos. So that's perfect. This is now what we can use to very easily load into our vector database in the second part. Of course, this step could be skipped if you already have sort of a folder with all of the pictures that you actually want to index. But let's get into actually setting up our vector database. And to do this, we'll be using ChromaDB, the one that kickstarted this entire project. And ChromaDB now has sort of this integration with OpenCLIP embedding models that we went over a little bit earlier. I have a few more things here on what those are in case you want to look at different references. But essentially, ChromaDB's OpenCLIP integration currently uses this model, the CLIP VIT-B32 Leon 2BS34BB79K embedding model. So a little bit of a mouthful there, but essentially all this is it's a CLIP-based model that was trained on the LAION or Leon 2 billion English subset of Leon 5B. And Leon specifically is a large-scale open dataset that contains about almost 6 billion filtered image text pairs. And it's essentially a big resource that you can use to both train and sort of put together different models that are useful for different image classification or other image manipulation tasks. So specifically, the Leon 2B English has about 2.3 billion samples of these text image pairs. And so to get everything working here, we'll be using ChromaDB's API. And all I need to do is first instantiate the client. You can use chromadb.persistent-client and then path over to where you want that to be. I just have that as image_VDB. And then also your image loader. So you're going to do that similarly with ChromaDB. You can just instantiate that. And then also instantiate the embeddings model. So for this, it's going to be OpenCLIP embedding function. And then you pass all that through the Chroma client with get or create collection, give it a name, path towards the embedding function, and path towards the data loader. And then that will create another folder right here, which we named ImageVDB. And that's where your vector database for all of these images is going to sit. So very simply, that's all you need to do to set this up to be able to start inputting some pictures. Actually getting the images into our vector database from the file is not too bad. We can use this method add that takes in IDs and URIs. And so IDs are just going to be literally, 1, 2, 3, 4. It can be any sort of ID that we want. We just have to define it. I'm just going to use a string of 1 up to 1,000, all integers. And then the URIs are uniform resource identifiers, which in the case of this is just going to be the path actually to the image. So to do this, very simply, just start a list of IDs and URIs that are both empty, and then we iterate over the entire thing, append either a index number and then a path to the IDs and URIs, and then we pass that all into the image VDB, which we created up here with IDs equal to IDs and then URIs equal to URIs. And then that's all we got to do to actually put those into the vector database. Then what we can do is use this .count method, and it will return back 1000, meaning that all 1000 entries are in there, and that's perfect. Chroma also makes actually querying the database pretty simple as well. So to do that, I wrote this quick helper function of QueryDB. It'll take in the query, which is going to be our raw text from the user, and then I have a results argument here, which I have set to 5 automatically. And then all we need to do is take the same image VDB, which we defined back up here, which we used in add here, but now we can use the query method. And then all we have to do is pass in the query texts, which in our case is going to be our query from the user, how many results we want to show up with n results, which in this case will be 5, and then what information we want to be included when it's actually being returned. So I want the URIs to be included, because from the URIs, that's how I can get the path to actually display the pictures, and then also the distances. And the distances are going to be the actual calculated distances between your query and the embedding of the photo. And so that's sort of the measure of how similar your query or your text is to the photo. So let's go ahead and test this out. And to do that, I have this function print results. And so that's just going to enumerate over the ID and the URI of each result that is returned from the query. And then it's going to print the ID, it's going to print the distance, it's going to print the path. And then because we have the path under the URI, we can use a different package to just display that image with the IPython package, I believe. Yes, IPython. And so with that, we'll display it and then also just print out a new line. So if we put in leather jacket and use the QueryDB function, that leather jacket's going to go to this query, which is then going to be put into the query texts to return the results. And then that's all going to be spit through the print results. And so then that returns this. We can see that from our leather jacket, we have now 5 different pictures of people wearing leather jackets. And that's great. We can see what ID they are. We can see the distance that was calculated between the picture and the text. And then we can see the path where it actually shows up actually on file in that folder. So perfect. This is great. It's working. Let's try something else even here. So let's say like red tops. Look at that. Red tops. That is great. So this is working perfectly now. So now that we have the retrieval out of the way, what we need to do then is set up the augmented generation part of that. So essentially this is going to follow this order. The user is going to submit a raw text input, could be a question, could be a query, etc. It's just going to be raw text. That input's then going to go through the retrieval function, similar to how we had just, red tops here. And then it will try and pull relevant images from the vector database to match the user's input. Those images then, along with a prompt, will be fed into a vision-capable model, where that's where the augmented generation is going to come in, as the model will use the images and the prompt as context to respond as a final output. To make things easy for us, we're just going to be using GPT-4o. So as of the time of recording this, this is OpenAI's latest model with both audio, vision, and text capabilities. So it can take in all of these modalities at once and then respond with audio, vision, or text as well. And essentially, we're just going to be passing in the image data along with a prompt, and it's going to return some other text for us as well, but it's going to be able to use all of that as context. To put this together, we're going to be using some LangChain framework, and I have a link directly to their documentation about multimodal prompts, but this is how I set up everything myself. First, you need to instantiate the language model. To do that, you can use the chat OpenAI function, path over to GPT-4o, set the temperature to whatever you like. Generally, I just keep it at 0, and then I have that saved in GPT-4o. We're also going to use a quick string output parser so that we can convert the actual response from the model directly just to a pure string without having to path into anything strange there. And then here's where we're actually going to be doing a little bit of inserting the context dynamically into the chat prompt. And so right here, we're seeing that we're using a chat prompt template from messages. And what we're going to be able to do here now is first set up a system message. And so this is following the simple flow that OpenAI system user response messages tend to take. And so what we're doing here is pathing into the system first. And so the system prompt is going to be, you're a helpful fashion and styling assistant. Answer the user's question, using the given image context with direct references to parts of the images provided. Maintain a more conversational tone, don't make too many lists, and use markdown formatting for highlights, emphasis, and structure. Something pretty simple. And then the actual user prompt that we're going to pass to it is then going to be first 3 instances of things. So the first one's going to be text. The text is going to be, what are some ideas for styling? And then in brackets here, we have user query. That's where we're going to dynamically pass through the actual input from the user into this. And so then for the second 2 things, this is where we're going to put in more of that context. And these are actually going to be image URL types. And from that, what we can say is this thing that I got from just right here from LangChain's documentation will essentially say that it's expecting an image that's going to be a JPEG of base 64 encoding. The JPEG doesn't necessarily matter here or there. What matters is the base 64 encoding. And then these are the placeholders where we're going to take both of the image data once we've encoded into base 64, which we'll get to in a bit, and dynamically insert in there. Then all we do is create the chain, which is going to be the image prompt. That's then going to get passed to GPT-4o, and it's going to get passed to the string output parser. So perfect. This is setting up our RAG prompt, essentially using LangChain with GPT-4o. This leaves us then with solving the issue of how do we actually format and get the user query, the image data, and pass it through. So that's what we're going to tackle right here in formatting query results for LLM prompting. Essentially, to input the images in as context, we first need to encode them to base 64 for the LLM to be able to interpret it. And base 64 is a way of encoding data using 64 different ASCII characters, which are safe to use in text-based systems. And the encoding essentially will transform the binary data of the image into a text format that can be easily transmitted and stored. And so when you encode an image in base 64 for a vision model, it's usually because the model or the system hosting the model requires the image data in a text format. This ensures that the data is handled very consistently across the different platforms and different languages that might be processing it. So by encoding our image in base 64, we can convert it then from an image to a string of text, making it much easier to send and process without having to worry about different data issues. So the function below that I've written here will essentially do that and create a dictionary along with the original user query to pass back into our chain. Our chain here is going to expect an input of a dictionary that can path to the user query, the image data, and the second image data. So let's go through this function and explain how that's happening. So it's going to take in 2 inputs, the data, which is going to be the results of our query, and then also just the user query. We're going to start an open dictionary here that has absolutely nothing. First thing that we're going to do is add in this key user query and then the value of user query, which is what's going to get passed in. And so that will then start this. So this will be the first line here. And then we're going to get the paths to the images from the results and the URIs there. And then we're going to use the base 64 package to do some encoding. So that's what these few lines are doing. We're opening up that in binary, the actual image in binary. We're going to read it. And then using base 64, we're going to encode it into this nice long string of text. Do that both times, and then add it on to the key of image data 1 and image data 2. So now we're going to have this full dictionary here that'll have the keys of user query, image data 1, image data 2, and then the values of the actual prompt. So what are some ideas for styling, X, which we'll get to soon. And then the 2 base 64 encodings of the first image and the second image. And this is what our chain here, the vision chain, is going to be expecting as input to actually be able to run it. So that's perfect. This will work nicely when passing in our results from the retrieval and then also the query. So now all we have to do is put it all together. So as mentioned, we now have the retrieval step already defined. And then now we also have the generation step here defined. So putting them together looks a little bit like this. I just have some fancy little markdown things here, which will display and look nice when we actually start to run this. But we're going to take the query as an input. And then very simply, we're going to use our QueryDB function with the query that we input. And we're only going to grab 2 results for this example. And then that's going to be saved in results. We're then going to format both the query and the results with this function here, the format prompt inputs, and that's going to be this function that we just went over, and then that's going to be the prompt inputs. And then what we can do is get the response from the model by using the vision chain and invoking it with the dictionary that we made from prompt inputs. And so that will map pretty much all of these keys and values into here, into where they're supposed to be very dynamically with what we've put, and then pass that all to the language model and get the language model's response out. we're then just going to grab the URIs from the results that we had here to display some of the pictures and then also print out the response. So let's give this a shot. So Fashion Rag is at your service. What would you like to style today? I'm going to say brown pants. And so now that's going to kick off the retrieval and then also the generation step. So let's give this a second and see what it comes up with. Great, so this is what we got back. So Fashion Rag is at your service. We wanted to style some brown pants. And so it grabbed two pictures. I'm seeing brown pants in both of them, so that looks phenomenally. So let's see what the language model was actually able to generate with both of these pictures plus our prompt of styling brown pants. So it says, styling brown pants can be quite versatile and chic. Here are some ideas inspired by the images you provided. First is a monochromatic look. First image, brown pants are paired with a matching brown blazer and a black top. I would say that's pretty correct there. It creates a sophisticated and cohesive look. You could add a statement belt, like the zebra print one shown, or add some flair and break up the monotony. She does have a zebra print belt on. I didn't even realize that at first. So it says a few examples there. The second one, a little bit more casual chic. The second image shows a more casual approach with brown shorts paired with a white top. Perfect for a relaxed yet stylish look. Then it also gives me some additional styling tips, different footwear options and accessories. It says, by mixing and matching these elements, you can create a variety of stylish outfits with brown pants. So this is great. This has retrieved exactly the right pictures and then use them as context along with my input to generate a response. So we now have a fully functioning multimodal RAG setup. So to sum things up, we now have the ability to actually use databases with other modalities other than just text for our retrieval augmented generation flows. This is allowed through language models with different capabilities of modalities, such as GPT-4o that can process images, and using things like CLIP embedding models with vector databases such as Chroma's. So super cool. We can take our user query, retrieve relevant photos from the text, and then pass all of that to a language model that can actually process all of that to generate our output. So, of course, all of this code is going to be available in the description below, along with some other resources. If you enjoyed it, leave a like. If you've got some questions, ask them in the comments. And of course, feel free to subscribe if you found this useful. Thank you.